All right, so first derivative test. So we're learning to use the first derivative test to determine the locations where a local max or minimum will be on a curve. And we're learning to use the first derivative test to determine the intervals where a function is increasing or decreasing. Okay, so it makes sense that hills and valleys, so a hill being a maximum and a valley being a minimum, sometimes they call the hills peaks and valleys, depending on the textbook, occur where the slope of the tangent is horizontal or equal to 0. The first derivative test states that a local maximum or minimum will occur where f prime at x is equal to 0 if the derivative changes sign, so from positive to negative or from negative to positive. So here's a definition. If f prime at c equals 0 or f prime at c does not exist, and this is normally we do another 2 lessons in a non-pandemic year, but this is something that the ministry suggested we leave out is sketching rational functions. So we're just going to do polynomial functions this year. So does not exist would be like where the denominator was 0. Then c is a critical number. So this year we're only worried about if f prime at c is 0, then c is considered to be a critical number. Okay, critical because it's where we could have a maximum or a minimum. Only critical numbers can be local maximum or minimums, but not all are. And that's, again, the not all are is because sometimes f prime at c does not exist. Can give you a max or min, but also cannot give you, in some cases, a max or min. So for us, this year, it's easy. If f prime at c is 0, it's actually, that's not true. Sometimes it'll give you a, you'll see this after the second lesson, it will give you a point of inflection, but we won't have to worry about the does not exist part this year. So we already looked at the little picture here. If f prime at x changes from negative to positive, so that's this case here, the slopes are negative and then they're positive, then you have a minimum. And then if the derivative changes from positive to negative and 0 in the middle, then you have a maximum. Local maximums and local minimums are called local extrema. So that's kind of an umbrella term. If it says find the local extrema, it wants all maxes or minimums. So here's an example of a local maximum. And they've got the little slope of the tangent is positive, 0, negative. And c would be considered a critical number. Here, the slopes would be negative, then 0, then positive. That would be a local minimum. And here you can see we have f prime at c equals 0, but we don't have a maximum or a minimum. Okay, so these special points here are what you're going to learn about this afternoon. And the second derivative tests are called points of inflection. And the whole lesson this afternoon is about how to find those and combine them with these to draw a nice graph. And then there's an example of a graph, which will be what we're learning how to do today, where we have a maximum, a minimum, and this is a point of inflection, which you're going to learn about this afternoon. This is a maximum, and this is a minimum. All right, so now we'll actually just get to it. So find the local extrema of the function y equals x cubed minus 9x squared plus 24x minus 20 by applying the first derivative test. Make a sketch of the function. Okay, so the first thing you're going to do is find y prime in simplified factored form. So y prime is 3x squared, so I'm just using the power rule, minus 18x plus 24. And I see a common factor of 3 in all the terms, so I'm going to common factor out 3. And I would get x squared minus 6x plus 8. And then this, I would check and see if x squared minus 6 plus 8 can be factored. If it could be, it would be a simple trinomial. So there would have to be two numbers that multiply to 8 and add to negative 6. Anyone know what they are?
Is it -4 and -2?
It is.
Whoa.
Okay, so now I've got the derivative in simplified factored form. And now we want to set it equal to 0 to see if there's any critical values. Okay, so set y prime equal to 0. And because we have it in simplified factored form, it's really easy to see that this equation is true if x happens to equal 2, because 2 minus 2 would make 0 in that factor, and then x equals -1 would make 0 in that factor. And if either one of those is 0, then the whole thing becomes 0 because it's all multiplying. So that tells you, any questions?
-4 to +1.
Oh, sorry, my bad. I have no idea what happened there. Thanks, guys. Okay, x equals 4. So that means that, so therefore, x equals 2 and x equals 4 are critical numbers. So you probably did something like this in advanced functions with Mr. Zalawiga. We use the critical numbers to split up like a whole x-axis into intervals. So from left to right, if I was going from left to right, I'd come across 2 before 4. So say here's 2, here's 4. So the intervals that I'm going to do, so first of all, we'd say we're going to do the first derivative test. And I'll let you use capital F, capital D, capital T instead of writing out first derivative test every time. But for the first time, for sure, I want to write it out so you know what it is we're doing. First derivative test on, and then we want to choose the first derivative that's in simplified factored form on y prime equals 3 times x minus 2 times x minus 4. And then we're going to test the sign of y prime in the different intervals. So this interval here can be described as the interval from -∞ to -2. I'm using interval notation with the round brackets. And then we want to know what happens when x equals -2. Sorry, my bad. I don't know why I'm doing this. I'm thinking about my vaccination appointment. -∞ to +2, sorry. And then x equals +2. And then my next interval is 2 to 4. And then what happens when x equals 4? And then my last interval is 4 to infinity. And then I'm going to make a little chart. As neatly as I can. You don't have to use a ruler for this part. And then what I'm doing is I'm testing the sign of y prime, whether it's positive or negative. I'm going to do a little representative picture. And then I'm going to make a conclusion. So this probably looks a bit familiar from advanced functions, at least the interval style and the chart style here and what's happening according to signs. So if I'm looking at my first derivative, I know 3 is always positive. So it's not going to affect the sign. So I pick a representative number that's in the interval negative infinity to 2. 0 is an easy choice to make because it fits in this interval. So if I pretended to put 0 into x minus 2, that would make x minus 2 negative. And then if I put 0 in for x and x minus 4, it would make this factor negative as well. So positive times a negative is a positive. And that means that the slopes of the tangent are going to have a positive slope in that interval. So there's my representative picture there. And my conclusion is that the function would be increasing over that interval. Positive slope increasing, function will be increasing. At x equals 2, y prime is going to be 0, which means the tangent was going to be horizontal. I'm not going to make a conclusion yet because I have to wait and see what the sign of the derivative is going to be on the other side of my horizontal tangent. So now I'm going to test the interval 2 to 4. So I'll choose 3, I guess, because it's right in the middle. So if I put 3 into this factor 3 minus 2, that would make 1, which would be positive. And 3 minus 4 would still be negative. So I have 2 positives and a negative, make the first derivative negative, which means my tangents would have a negative slope, which means I would be decreasing over that interval. And then because on each side of the place where the tangent is 0, one side I'm increasing, the other side is decreasing, I have a local, or just a maximum, it is local, but I don't want to write too much in that little box there, a max at, now we know the x value for our maximum is 2. How would I figure out the y value for my maximum?
Put it back into the original equation.
Right, into the original. So I'm going to move this back up here. So I want to find y at 2, not y prime, y at 2. So that's going to be 2 cubed minus 9 times 2 squared plus 24 times 2 minus 20. And you can put that into your calculator. Is it?
I think so.
Nice.
Yeah.
Yep, I got 0. So a maximum at 2, sorry?
Oh, sorry, I got my mic still on.
Okay,
All right.
all right. Everybody good? Maximum then at 2, 0. Okay, so back to our chart at x equals 4. Again, we have a horizontal tangent. From 4 to infinity, we could pick a number like 5 fits in there, which would make this factor positive, but also this one. So they'd all multiply together to give a positive first derivative, which means our tangents would be increasing. So decreasing, 0, increasing means we'd have a minimum at 4. And then again, up here, we'd have to find y at 4. So 4 cubed minus 9 times 4 squared plus 24 times 4 minus 20. Negative 4.
That's what I got too.
Yep. Okay. Confirm with me. All right. So now we are going to draw a sketch. Okay. So it's just going to be a sketch. So I'm going to use a ruler for my XY axis. And then I'm going to kind of look at these. We have a 0 and a negative. So I'm in my sketch, I'm going to have more room in the negative part of my Y axis than in the positive part. Remember, this is just a sketch. It doesn't have to be to scale or anything like that. So then I'm going to choose to place my 2 points. So 2, 0. So if I put a point here and I want to call it 2, 0, so I just put my point on that axis and label it 2, 0. And then 4, negative 4. Four, negative 4. So any point you put on, label it. Okay. One other thing, if one of the points we put on from our two charts, eventually just one chart this morning, isn't the y-intercept, we can always put the y-intercept on if it fits, or just keep it in mind. Does everyone realize that the y-intercept would be negative 20? So if we sub 0 in for x, we'd get negative 20 for y. So keep that in mind, okay, when you're drawing it, like negative 20, it's going to be way down here. So you're not going to be crossing the y-axis until I can put it on, but it's not really to scale. But here's my 0 and negative 20, which is my y-intercept. So keep it in mind. All right, so following my instructions here, I'm increasing from negative infinity to 2, and I have a maximum at 2, 0. So I'll draw in having a maximum at 2, 0. Then I'm decreasing from 2 to 4 to a minimum at 4, negative 4. And then after that, I'm always increasing. So there's my arrow, always increasing. And here, always decreasing. And see, I didn't go as far as my y-intercept, but I didn't cross through the y-axis, because that would have been incorrect. I don't cross through the y-axis till I get down here at negative 20. So there's a sketch. It is just a sketch. It's not to scale, but it's a sketch that has the important maximum and the important minimum on it. Using the first derivative test, then I always go back to my chart and make sure it makes sense. So I want to make sure that I'm increasing from negative infinity to positive 2. So yes, always increasing to there. Then I'm have a max, decreasing from 2 to 4. Yep. And then always increasing after that. Yeah. Okay. Any questions? All right, try another one. Find the local extrema of the polynomial function by applying the first derivative test. Is it possible that the sketch below can be the function? Well, that should be f at x, not just x, f at x. All right, so we'll do the first derivative test. So we'll find f prime at x first. So it's going to be 4x cubed minus 12x squared plus 8x. Then I have a common factor of 4, I see. Oh, 4x, sorry, 4x. So if I common factor out 4x, I'm going to get x squared minus 3x plus 2. So that I've common factored. Now I'm going to check whether the trinomial can be factored. If it can, it would be a simple trinomial. So I'd need two numbers that multiply to positive 2 and add to negative 3. Negative 2 and negative 1.
I like it.
Yep. Okay, so now we're going to set it equal to 0. Don't forget to show that step. And what values of x make that true? Multiplying all those 4 times x minus 2 times x minus 1. What values of x would make that 0? I think these two you'd all get. Which one am I missing?
0.
Right, this x here, x equals 0. So therefore, the critical numbers are x equals, so let's put them in order from smallest to biggest, because that's how we're going to use them for the first derivative test. So 0, 1, and 2 are our critical numbers. And the critical numbers are what you use to do your first derivative test. Oops. All right, so now we're going to do the first derivative test. So you can use capital F, capital D, capital T, first derivative test on f prime at x, and we want the factored form equals 4x times x minus 2 times x minus 1. And again, we're cutting up our x-axis into the interval from negative infinity up to 0, from 0 to 1, from 1 to 2, and then from 2 to infinity. Okay, so our first interval is going to be negative infinity up to 0, and then x equals 0. Our second interval is going to be between 0 and 1. Our next interval is going to be between 1 and 2. And our last interval is going to be between 2 and infinity. And we want to know the sign of f prime at x, a representative picture, and a conclusion. So again, 4 is always going to be positive. It doesn't really affect the sign of our derivative. So for negative infinity to 0, I might choose negative 1, which is going to make x negative, x minus 2 negative, and x minus 1 negative. So 3 negatives multiplying together make a negative. So my slopes of the tangents are going to be negative. And in that interval, I'm going to be decreasing. When x equals 0, the derivative is equal to 0, which means my tangent's horizontal. From 0 to 1, I could choose a number like a half, which would make this plane x positive. But this factor would still be negative, and so would this one. So overall, if I multiply positive times negative, I would get a positive first derivative, which means I'd be increasing, which makes this, you can just see it with the pictures here, a minimum. At 0, and usually it's really easy to sub 0 into, you can just do it by inspection, f at 0 equals 0. Because all the x's become 0. So a minimum at 0, 0. At x equals 1, again, the tangent is horizontal. 1 to 2, that would be a number like 1.5. So this is positive. This is still negative, but this one becomes positive. So overall, the sign of the first derivative is going to be negative. We're decreasing. Which means this is going to be a max. At 1, f at 1, which is going to be 1 to the 4th minus 4 times 1 cubed plus 4 times 1 squared, which is 1. Maximum at 1, 1. Then at x equals 2, 0, horizontal tangent again. 2 to infinity, that's a number like 3. So it's going to make x positive, x minus 2 also positive, and x minus 1 positive. So the whole first derivative is going to end up being positive, increasing. So we have a minimum at 2, and then let's find f at 2. 2 to the 4th minus 4 times 2 cubed plus 4 times 2 squared. Got 0.
Yep.
Okay, and in this case, we're not asked to draw it. We're asked to see whether this could be the sketch of it. So we can use our first derivative test. In this sketch, are we decreasing from negative infinity to 0? Yes, decreasing to 0. Do we have a minimum at 0, 0? Yes. Are we increasing between 0 and 1? Yes. Do we have a maximum at 1, 1? Yep. Decreasing from 1 to 2, yes. Minimum at 2, 0, yes. Increasing from 2 to infinity, yes. So is it possible that the sketch below can be the function? Therefore, the sketch can be the function f at x equals x to the 4th minus 4x cubed plus 4x squared. Any questions for that one? Okay. Find the local extrema of this function by applying the first derivative test. Make a sketch of the function. Okay, so we'd find y prime first. So it's going to be 4x cubed minus 12x squared minus 16x. Then you can common factor out 4x. Then you can hopefully factor that trinomial. So multiply to -4 and add to -3 is going to be -4 and +1. Set it equal to 0. Don't forget that step or you'll lose a mark. Which means our critical values are going to be 0, 4, and -1. Put them in order, so -1, then 0, then 4. And then we want to do the first derivative test on y prime equals 4x times x minus 4 times x plus 1. And then make our table, which is how you do the first derivative test. So our first interval is going to be from -infinity to -1. And x equals -1. Our next interval is from -1 to 0. x equals 0. Then the interval 0 to 4. And then the interval 4 to infinity. And then we're looking at the sine of y prime. Little picture and a conclusion. Four is always positive. So we choose an x in the interval negative infinity to negative 1. So it could be negative 2, which would make x negative, x minus 4 negative, and x plus 1 negative. So that's going to overall make my derivative negative. We're decreasing over that interval. Then when x equals negative 1, our tangent's going to be horizontal. From negative 1 to 0, that would be like having negative a half. So that's x is going to be negative still. So is x minus 4, but x plus 1 is going to be positive. So then overall, my derivative, the sign of the first derivative is going to be positive or increasing, which means I would have a min at negative 1. And then I have to go up to my function and sub in. So y at negative 1. So that's going to be eight. So a minimum at negative 1/8. You guys get 8?
Yep.
Yep. Okay. So 0, horizontal tangent. From 0 to 4, I could pick a number like 1. So that changes x to being positive now. This is still negative, and this is still positive. So overall, my derivative is going to be negative. We're decreasing over that interval, which means we're going to have a max at 0 and 11, because it's really easy to sub 0 in. And then if we set 4 in, we'll get a horizontal tangent. 4 to infinity, so pick a number like 5, positive. Now this one's positive, this one stays positive. So our first derivative will be positive or increasing. So we're going to have a min at 4. Four to the 4th. Oh, that becomes 4 to the 4th as well. Negative 117.
That's what I got.
Okay, great. Okay, so you can see this sketch definitely is not going to be to scale, but it's just a sketch. So now we're going to make an XY axis. More room at the bottom because we're going down to negative 117. It's a sketch, so it doesn't have to be to scale. As long as you label every point you put down, it doesn't have to be to scale. So -1 and 8, I'm going to put like here. Zero and 11, I'll put here. And then 4 and -117, I'll put down here. And then I just kind of follow my first derivative test. I'm decreasing from -infinity to -1, where I have a minimum. So something like this. Then I'm increasing up to a maximum at 0 and 11. So try that again. Start going up to a maximum. And then I'm decreasing from 0 to 4. Ultimately getting to a minimum at 4 and -117. And then I'm always increasing after that. Arrows on the ends. And there's my graph. And then just make sure it agrees again. So decreasing from -infinity to -1, increasing from -1 to 0, decreasing from 0 to 4, and then increasing after that. Try to make your curve look smooth. There'll be more, the points of inflection will help you make it look even better when you look at the second lesson for today. Any questions for that one? Anyone need more time? Okay. Our last example, find the local extrema of the function by applying the first derivative test. Make a sketch. So f prime at x is equal to 6x squared minus 6x minus 12. 6 is common. We've got a simple trinomial that we can factor. So two numbers that multiply to -2 and add to -1, -2 and +1. Set it equal to 0 to find the critical values or solve for the critical values. So therefore, critical numbers are x equals -1 and 2.
You need us to put that arrow in between.
Nope.
Okay.
And then we just want to do the first derivative test on f prime at x equals 6 times x minus 2 times x plus 1. So our first interval is going to be from -infinity to -1. X equals -1, -1 to 2. So we want to know the sign of f prime at x. Picture and the conclusion. So from negative infinity to -1, I'm going to choose -2, which is going to make this negative and this negative as well. So altogether, 6 is always positive. I have positive, increasing, x equals -1, 0, horizontal tangent. In the interval -1 to 2, I could choose 0. Changes this to positive. So overall, I'm negative or decreasing. So I would have a max then at -1, and then f at -1. So it's going to be -2 -3 plus 12 plus 12. 19. Yep. And then x equals 2, 0, 2 to infinity. So like a number like 3 makes them all positive. So we're increasing, which means we have a min at 2, f at 2, 2 times 2 cubed, minus 3 times 2 squared, minus 12 times 2 plus 12. So that's going to be I accidentally wrote that as a 12. I thought that was large there. Minus 24 plus 12. -8.
That's what I got.
Excellent. Okay, so there's our, got a max and a min. We can make our sketch. Label your x and y axes when you do your sketch. So -1 and, oh, positive 19. I probably should have made this lower down. I'm going to correct that. So -1 and 19, put up here, label it. And positive 2 and -8. So we're increasing up to here, where we have a maximum. Oh, and then we should be aware of our intercept is at 12, our y-intercept, which I can put on. So f at 0 is 12, which is the y-intercept. So if this is 19, say this is 12-ish. So that's my y-intercept. Just another helpful point we can have on there. All right, so this is a maximum. Then we're decreasing. to a minimum. Try to make it as smooth as I can. Decreasing to a minimum and then increasing. And then just always double check your picture with the chart, and then this afternoon it'll be with the two charts. But we're increasing from negative infinity to -1. Yep, always increasing. Maximum at -1 and 19. Decreasing from -1 to 2. Yep. Minimum at 2, -8. And then always increasing after that. All right, that's the first derivative test. All right, so it's very important that you watch the video. What happened to me was I put a little introductory video that I found on YouTube that was really good, kind of like the whiteboard thing. That shows you what the second derivative is about, which is really good. Sorry, I'll just get out of this. Stop recording.